do that? So I'm starting the live stream right now.
Yeah, I can do that.
Okay, I think everything is set up correctly now, so we can get started. So I was hoping to start a bit earlier this time. I think in general, we'll strive to start maybe 5 to 10 after, and then take a break in the middle a bit longer, but unfortunately we had to start around 15 past right now. Okay, so welcome to the second lecture of digital design and computer architecture this semester. Yesterday we talked about the introduction and basics. So hopefully you're motivated that there are a lot of interesting things going on right now in architecture, and there are more interesting things to come actually in the coming few years as well as a decade. And we're going to learn the basics to actually how to enable those bigger things going into the future, hopefully. Okay, so today I'm going to start with some puzzles. It's going to be fun. It's actually more fun when you have an in-person class, but let's try to do it over here. So let me show you what the puzzles are. So I'll ask the question, what is this? Some people may write in chat, although it takes longer. I assume many people who are in Zurich know what this is. Yeah, I think I see some people saying Stadelhofen. Yes, and they're correct. So this is Bahnhof Stadelhofen in Zurich. It's a very nice place, I think. It may look a little bit old underneath right now. And this is another view of it, the top view. You can see that there's some interesting construction that has happened over here. Some people say a bit violent, maybe. Okay. So the next question is, what do the following have in common with the Bahnhof Stadelhofen, basically? So this is Gare do Oriente in Lisbon. It's a beautiful building. And I don't expect to see answers over here because I cannot really keep track of them, but feel free to. Yeah, somebody said the architect and they're correct, basically. This is Milwaukee Art Museum. It kind of looks like Bahnhof Stadelhofen, as you can see over here, right? The angles and what it resembles looks like what we saw in Bahnhof Stadelhofen. This is Athens Olympic Stadium, City of Arts and Sciences in Valencia. And this is probably someone paid more money for this, Florida Polytechnic University. And sometimes universities make the mistake of showing off buildings as opposed to showing off their science. As a result, you get things like this. But it's certainly good to see it. But it's better to invest that money into science and scientists in general, I would say. Okay, and this is the Oculus in New York City, as you can see, which was supposed to be something like this, actually. But the folks in New York City said, okay, we're not paying any more money for this. But basically, all of this, what all of these have common is really the architect, as a couple of people suggested. I think I couldn't see all the responses over here, but this is the next question. What do all of these have common with Bahnhof Stadelhofen? And that's really the architect. And the architect is an ETH alumnus. He got a PhD in civil engineering a while back. And basically, this is what's written. The train station has several of the features that became signatures of his work. Straight lines and right angles are rare. And this is Santiago Calatrava, as what some of you mentioned And I will say that your first computer architecture assignment is to go visit the closest Calatrava building to this classroom, except it's an online classroom, so you have the option to actually go and visit whatever you find next to you. And if you're in New York, it's going to be something else probably than Bahnhof Stadelhofen. And for those who like a challenge, you can actually find the furthest building that was designed by Calatrava to this classroom or to wherever you are. That should be this, by the way, not his. And I would encourage that you appreciate the beauty and out of the box and creative thinking that went into the design of that building. Think about the trade-offs in the design, strengths, weaknesses, and goals of design, and derive principles on your own for good design innovation. And in the end, just like building architecture, the computer architecture is all about trade-offs in design, getting some metrics to a level that is satisfiable or that satisfies the design goals. And there might have been some design goals in these designs that we're not going to talk about. This is not a real architecture course. This is a computer architecture course. We will talk about the design goals in computer architecture later. But I want to motivate with this real life examples of real architecture that the real architecture actually has similarities to computer architecture because you're also making trade-offs there. And again, there's no due date for this. This is on your own anytime during this course. I would suggest later during this course or later, even after this course is better, you can apply what you learned in this course and maybe think out of the box. Maybe you can improve the designs as well. And in fact, in the past, people have taken my classes. They went and visited some of these places that were on the pictures, especially the Oculus tends to be popular in New York City, partly because New York City is probably a good tourist destination. But I received pictures of these people from the Oculus, and they in general, they agree that it's one of the best places to visit. But we'll have some story about that in a little bit in this lecture related to the design trade-offs. Okay, but first, today's first assignment is something else, and we're going to do that together. Basically, we're going to try to find the differences between this and that, where this is the Stadelhofen station, as you can see, and that is this, essentially. This is some random train station. Somebody figured out that this is a train station in Germany. I don't care, basically, but in the end, it's like a normal train station, right? It's nothing out of the ordinary. It's maybe kind of boring, but it works, I guess. It's not that bad, but it's clearly it doesn't have the artistic value that this one has. And again, this could be dependent on the person's aesthetics. So some people may feel more comfortable in this one than this one. So they're basically metrics. My point is you have metrics to evaluate these things with. And you can list these differences maybe after you complete the first assignment. So let's take a look, basically. So these are two different designs, and designs can be evaluated based on some evaluation criteria. And evaluation criteria are essentially the metrics with which you can evaluate different designs. And we're going to talk about a lot of computer architecture, digital design concepts, and you always have different options for design, and those options lead to different trade-offs that lead to different values in these metrics. And that's the whole point of this part of the lecture. Let me put it that way. And let's take a look at some of the evaluation criteria. This is certainly not exhaustive, but some of the criteria could be functionality. Does it meet the specification? Somebody specified a train station to operate in some way. Does it meet that? Is it reliable? Does it occupy too much space or too little space? Area is usually related to cost, for example, or something else, right? Maybe you just don't have enough area regardless of how much cost you pay, and as a result, you need to put this Oculus in the middle of New York City in a very tight space requirement. Cost, always a constraint in any design. Expandability, can you expand it? What is the comfort level of the users? And some of these metrics now start becoming, okay, it depends on the person, right? And we see that also in computer architecture. You design a computer chip, doesn't matter what kind. It could be general purpose, special purpose, etc. And the metric could be performance on workloads. And the performance will be dependent on what workload is executing on the chip. For example, a GPU would be great at executing very parallel workloads that can be parallelized nicely, and also graphics workloads, but it may be terrible at executing very irregular workloads. So comfort level is, in this case, the workload is similar to users, and the comfort level is the performance you get, right? Or performance is similar to the comfort level you get. So I can basically draw a lot of parallels between real architecture and computing architecture, because real architecture also has workloads that may be happy, that may be wanting some sort of performance. And workloads tend to be users for real architectures. But it's not limited to users also, right? It could be, I don't know, it could be animals also, right? It could be, it depends on basically whom you design it for. And in general, real architectures, just like computing architectures, are designed for specific workloads, right? For example, and they're sometimes specialized, right? If you go to a school, you have classrooms in there, and classrooms are specialized for students and teachers, right? They're not specialized for a random person who may be doing, I don't know, some sort of design inside that classroom. So we don't know. So basically, there are a lot of parallels. Just like building architecture, computer architecture is also very heterogeneous, as we will see. Okay, I don't want to go through all of these metrics. You can imagine many, many other metrics also, like security or privacy, aesthetics. So there may be many things over here. So in the end, the takeaway is how to evaluate goodness of design is always a critical question whenever you're designing something. And this leads to performance, in quotes, evaluation and metrics. Performance may be real performance in terms of end-to-end execution time of a program, which we will talk about. But it could really also refer to any metric that is related to quantifying the benefits or downsides of a particular design. Okay, so a key question also related to this course. So we're going to talk about metrics later in this course, and we're going to talk about trade-offs. Whenever we introduce an idea, for example, we're going to talk about different trade-offs related to it. We'll try to cover the biggest trade-offs, of course, but we may not be able to cover every single trade-off related to an idea. And whenever you employ the idea in a particular setting, the trade-offs may change also depending on how the idea is exactly used. And we will talk about that when the time comes. So a key question also related to the subject matter of this course is, how was Calatrava able to design especially his key buildings, like what we have seen, the Oculus, for example? Clearly, you can have many guesses over here. Now we're getting into the mindset of the architect. Like, how does an architect work? And I think a computer architect is all similar to a building architect as well, because they do make a lot of trade-offs, both of them. And they need to really understand what they're doing so that they can design a building that meets the requirements, the design goals, and also that makes workloads or users happy, right? And here are some properties that I believe are apt to attribute to Calatrava, like very hard work, perseverance, dedication over decades, experience that's built because of the first bullet over here, creativity, out-of-the-box thinking, a good understanding of past designs. We talked about if you understand the past designs well, you can actually do better than the past designs. And I think that's where education really helps, when you that gives you the importance of the precedents, what comes before. Good judgment and intuition, that's usually very useful, since architecture and computer architecture are both some forms have an element of art in it, right? In the end, you're kind of predicting the future 20, 30 years down the road. And then strong skill combination, of course, math, architecture, art, engineering. This is applied to the real architect, of course. And you need to be able to have a good skill combination to enable this. And of course, there are some external factors or external/internal together factors. Funding helps. Usually, if you want to build something totally changing the paradigm, it takes a lot of money to actually enable it. Like processing in memory, for example, we discussed this yesterday. It takes a good chunk of money to change the paradigm of computation, and you need some funding. Of course, that comes sometimes with luck. And if you have initiative and entrepreneurialism, that also helps, right? And I think two other very, very important things that you can build in this course, well, in addition to the first several ones potentially, is strong understanding of and commitment to fundamentals and principled design. So I'm going to focus a lot on those two especially. But I think you will really be exposed to and hopefully develop and enhance many of these skills in this course. I cannot promise funding, but hopefully you'll be able to enhance a lot of other things that are over here, especially if you approach this course the right way, as a learning experience, as a formative experience, as we discussed last time, as opposed to just something you need to pass by taking the exam, right? I think you would be doing yourself a disservice if you actually think about just passing the exam, because there's a lot more to see over here, as you can see. And I think certainly these skills can help you in other parts of life as well, not just in computer architecture, computer science, or computer engineering. Okay, so we're going to focus a lot on the principle design and strong understanding of and commitment to fundamentals in the rest of this particular lecture. But hopefully we will see other examples like good judgment and intuition. We will talk about that when we talk about instruction-set architecture design. And one of the examples I will give you right now is usually it's better judgment to design your instruction-set architecture such that the specification is independent of the implementation underneath. If you tie the specification to the implementation, then you're really dictating some particular implementation. So you're reducing the freedom, essentially, from how you can actually design an underlying microarchitecture. So this is a good judgment, if you will, on how to design an instruction-set architecture. Of course, we could argue that this could be a principle design as well, right? Okay, so what is principle design? From the example I showed you from Calatrava, this is Calatrava's own words. To me, there are two overriding principles to be found in nature, which are most appropriate for building. One is optimal use of material. The other, the capacity of organisms to change shape, to grow, and to move. And this is from him, as you can see, and that's how he describes his work. Other people also describe the work as Calatrava's constructions are inspired by natural forms like plants, bird wings, and the human body. And I believe they're right. This is the Gare d'Orient in Lisbon, as you can see, and you can see that it's based on some humanoid blueprint over here. This is, I believe, his blueprint. And this is a special form of architecture that's principled. It's zoomorphic architecture. As you can see, it's the practice of using animal forms as the inspirational basis and blueprint for architectural design. And you can read more about it. I'm not going to go into it. But similar to this sort of architectural principles, we're going to talk about computer architectural principles in this course that are essentially very fundamental and that have lived through decades and decades, and that I believe are going to live through decades and decades going forward as well. Okay, so basically the next question is, what does this remind you of? I give you a lot of clues, I guess. This kind of looks like a bird. I didn't see anybody say it so far. Okay, somebody said bird, I see. Yes, this kind of looks like a bird, right? And that was kind of the intent, I think, based on public documents by Calatrava. Yes, it's the New York World Trade Center, but basically the structure of this World Trade Center that was built relatively recently is bird. And it was costly. We will talk about that. So basically the architect's answer is this. Oculus resembles a bird being released from a child's hand. The roof was originally designed to mechanically open to increase light and ventilation to the enclosed space, but because of cost reasons, that didn't come about. Basically, this was praised. Clearly, there are strengths. So with every design, you have strengths and weaknesses. And this has strengths also. I'm not going to go through all the strengths depending on the metrics, clearly. And you can see that this strength came externally from some person who was writing a newspaper article, a journalist basically. And this journalist says, "It is a pleasure to report for once that public officials are not overstating the case when they describe it as a design as breathtaking." So basically, I like how he expresses it clearly, because usually you don't get the best depiction of the truth from potential authorities, right? But in this case, this is one opinion, as you can see, right? It's not the strength is seen as breathtaking, but clearly there's criticism also, as you can see, and partly criticism comes from the design constraints as well. So basically, you can see that Calatrava's original soaring spike design was scaled back because of security issues. So you can see security being a problem even in real architecture, obviously. And in the name of security, Santiago Calatrava's bird has grown a beak. Its ribs have doubled and it's in number, and its wings have lost their interstices of glass, etc., etc. It may now evoke a slender stegosaurus more than it does a bird. So this is, I guess, a nice criticism, let's say. And this is, for your information, what a stegosaurus looks like, as opposed to a bird that some of you mentioned was a bird. So basically, no one is immune to these sort of design constraints. And these design constraints happen in computer architecture. It happens in building architecture. It happens in all sorts of engineering for sure. Whenever you're designing something, you run into design constraints, and it's really important to understand how you can create your design within the constraints you're operating at, and how you can maximize the metrics you really care about within those constraints. So you can see, for example, the design was further modified in 2008 to eliminate the opening and closing roof mechanism because of budget and space constraints. So security made it of a different shape, but budget and space got rid of the opening and closing of the roof that we saw in one of the universities earlier. And in the end, even though the budget was reduced, the transportation has been dubbed, hub has been dubbed the world's most expensive transportation hub for its massive cost of for reconstruction, $3.74 billion. Of course, I don't know if this is true. I just took this number from Wikipedia, which has references to articles, but I can guess that it's true, right? The design, usually a very out-of-the-box design that changes the paradigm somehow is costly. And that's true, as I mentioned earlier, in computing architecture as well. The design cost is always important. You cannot do everything at the expense of any cost. And even folks who may think that cost doesn't matter will in the end be limited by cost. So there are certainly governments who can put a lot of funding to something, maybe building a supercomputer, maybe doing even worse things. But basically, in the end, they run into the cost problem. And if somebody tells you that high-performance supercomputers do not have the cost problem, that's wrong. Basically, they are maybe less limited by cost, yes, because they're trying to optimize the maximum performance for a given workload, and they have less constraints about form factor. For example, this is a huge constraint about a form factor, right? If you don't see it, this is my cell phone. Huge constraint about a form factor. A supercomputer doesn't have that constraint. And as a result, its cost constraint is also much lower. But in the end, it's constrained by cost. And this is true, as you can see, for the Oculus as well. Okay, so that was hopefully an interesting discussion related to design trade-offs, metrics, and mindset. Let me give you another example of this. And this is basically what I used to do when I used to teach this class at CMU, actually. And I used to use this beautiful picture. How many people know what this is? Any guesses? I don't see anyone. Okay, maybe there's something, but I'm not able to see it. But this is basically the falling water. Somebody said falling water. Okay, maybe they went there. That's good. As you can see, it's constructed on top of a waterfall. And you can see that it's imitating the waterfall itself. There are two pieces of the waterfall here, and these cantilevers are imitating the two pieces of waterfall, etc. There are a lot of other things over here. Basically, but another answer to this is it's really the masterpiece of another famous architect, and that's this architect over here, who's another principal designer, and that is Frank Lloyd Wright, basically. And you can see that this is one of the most important places to visit before you die, according to some people, let's say. Of course, that's subjective in the end, but I visited this place many times, and I would argue that it's quite good, actually. And we can play the game of find the differences between this and that over here. And this is this, which is falling water, as I showed you. This is a more beautiful picture of falling water, I should say. And this is that. So clear the setting is kind of similar, but there are a lot of differences. So this is kind of a traditional design, let's say, and this is maybe more advanced design, let's say. I don't know. But basically, you can, again, evaluate these two designs based on many, many different metrics, which we're not going to do right now. You can do it on your own. In fact, I would encourage my students to go to falling water. It's only 1 hour, 15 minutes drive from Pittsburgh, where I used to teach. And essentially, whenever I went there, I learned a new thing, at least one new thing. And I think it's a good learning experience to really critically evaluate these designs whenever you go to those places. Basically, this architect did not design this one. They designed the previous one, and we will see why. But basically, the same questions apply to Frank Lloyd Wright, and I think these two architects have a lot in common in terms of what they did and how they enhanced the field and what kind of designs they produced. They basically were very principled designers, and they also had strong understanding and commitment to fundamentals based on their writing. You can see that, and clearly they actually did a lot of hard work, and their designs were always very costly, actually. because they actually challenged things out of the box, let's say. So building this falling water is actually not easy. And in the end, it was actually commissioned by the Kaufman family, who were the owners of the Kaufman stores in the US, which is actually a huge chain. So they were actually quite rich, let's say. And this family, in the end, had to tell Frank Lloyd Wright that, please stop, we're not paying you anymore. Basically, you can see that these designs can get out of cost also. But that's true for computing designs also, actually. If you're designing a supercomputer, you're again in the same situation. If you're designing a very cutting-edge, high-end processor, you're in the same situation. Somebody may tell you, okay, we're out of money. Pick whatever you think is the best that's going into these products, and convince that that is going to be the best thing going into these products, essentially. In-memory computation is another example. We will talk about, well, we talked about it yesterday. We won't talk about it a lot, but doing computation in memory is changing the paradigm like this, as opposed to doing processor-centric design that looks like this, let's say. At least that's my analogy. But it comes at a cost, as you can see. So basically, hopefully, you will be able to appreciate these sort of designs as well as you go through this course. And hopefully, you'll be able to enhance and develop many of these skills that are written over here. And if you can enhance your funding development skills, that's also good. Although I'm not going to explicitly teach you to that. But I think in a principled way of thinking and principled way of evaluating ideas enables you to also potentially a principled way of raising funding, let's say. Okay, let me leave it at that. Okay, let me describe the principled design that this architect had in mind. This is Frank Lloyd Wright. And Frank Lloyd Wright actually had a lot of opinions. He was a very hard-headed architect, if you will. But clearly, he created a lot of great designs. And he said architecture should be based upon principle and not upon precedent. And this was one of his biggest opinions. And as a result, he did not design this thing that resembles everything else. Basically, precedent says, precedent means what comes before, right? What precedes. Principle means what is principled. You don't care about what precedes. You just design based on what is right. And the architect did not design based on what precedes, which is, there are a lot of houses like this in rural America that looks like this. They're beautiful, I think. I don't mind living in them, but I would probably prefer living in something like this, right? It's much more eye-opening, let's say, and mind-stretching also. So this is more designed based on principle. And this is the design principle, organic architecture. It's a philosophy of architecture which promotes harmony between human habitation and the natural world through design approaches so sympathetic and well integrated with its site that buildings, furnishings, and surroundings become part of a unified, interrelated composition. This is a nice piece of writing, by the way. Okay, I'm not going to talk about this more, but basically, I already said that this is well integrated with the nature, with the waterfall on top of which it is built. Okay, so basically, we're going to talk a lot about principle design and strong understanding and commitment to fundamentals. Let me finish with some takeaways over here, at least this part of the lecture 2A. So in the end, computing architecture, just like building architecture, all starts from the basic building blocks and design principles. And that's why you're taking this course, hopefully, because it's a freshman course, right? And of course, you just don't learn just the principles, but you also learn the knowledge of how to use and apply them initially. And as you go through that, you will also figure out how to enhance them and adapt them to the conditions that you're dealing with. So this is very important. And that's one of the reasons why we have the labs. That's one of the reasons why we have the readings that are going to kind of push you to be critical. And in the end, it's important to keep in mind that underlying technology might change. This is true for, again, computing architecture as well as building architecture. In building architecture, for example, you may have steel versus wood, but in computing architecture, you may have, I don't know, mechanical systems versus electrical systems versus quantum systems later on. I don't know, maybe phase change-based systems, etc. But methods of taking advantage of technology bear resemblance. So you may still take advantage of, for example, caching, locality, which are principles that we will discuss, pipelining, to take advantage of the underlying material and technology, regardless of what the technology looks like. But of course, as you design the architecture and the algorithms together with the technology, you can do better, but some principles will remain for sure. And methods used for design depend on the principles employed as well. And we're going to talk about that quite a bit in this lecture. Okay, so basically, this is an example of how the same takeaways over here apply to processor chips. So basically, there are basic building blocks in a processor chip, and there are design principles. This end is duplicated somehow. I'm going to fix these slides. Somehow it's duplicated in all of the slides. You can see that there's a copy paste error over here. But basically, if you even though you may have different platforms, there are basic building blocks there, and design principles remain similar. Data centers, drones, self-driving cars, and high-performance supercomputers, TPUs. For example, you can have a systolic array doing matrix multiplication over here. You can have a systolic array doing matrix multiplication in the high-performance computing engine or a CPU, right? And also a different platform. So these platforms are all based on some design principles and basic building blocks. That's true for processing in memory engines also, as we discussed yesterday. For example, this FIM DRAM that was introduced by Samsung last year was essentially using an instruction set that is reasonably similar to any other instruction set that you would see in the processor that you're going to design actually for your labs, for example. It's a subset of the instruction set, in fact. So there's some basics that all remain similar, but of course, how you use those principles in the particular system that you're trying to design with the design constraints and the design metrics you're trying to achieve is what makes you a real architect. Of course, you need to learn the principles, but you also need to learn how you apply them. So let me give you some of the basic building blocks. These are things that we're going to see in this class, basically. They're electrons, transistors, logic gates, combination logic circuits, sequential logic circuits, storage elements, and memory. And then on top of that, these are basically relatively simple building blocks. We're going to start with a transistor, for example, as a building block, as an abstraction level. And then we're going to build logic gates and then logic circuits. And then on top of that, we're going to build like cores, caches, interconnect, and memories. And also, we're going to look at design principles on how to operate, how to design these things internally. So there's a lot we will learn basically in this course. We're going to go all the way from electrons. We're not going to talk about physics clearly because that's outside the scope of this course. Hopefully you all know the basics of physics from your high school. But we're going to start with the abstraction level of a transistor. Okay, so basically, let me jump into the course logistics for the rest of lecture 1A or 2A over here. But we have some reading assignments for this week. I mean, this week means you can start right now, and we're going to cover some of these things next week, actually. Chapter 1 in Harris and Harris, I would suggest reading chapters 1 and 2 in Pat and Patel. And again, as I mentioned yesterday, nothing is really required. You can get a lot of things in the lecture from the lectures, but I would recommend that you do the readings so that you can enhance your understanding. And there are always some things in the readings that I don't cover. It's because it's not possible to cover everything in the readings. And clearly there are a lot. Clearly there are a lot that's in the lectures that the buildings don't, that the readings don't cover, right? So I would. It depends. Basically, somebody's asking, would you recommend reading both books or one of them? I mean, it really depends on your bandwidth. Usually I will prioritize. So I will say chapter 1 is more important. We'll cover similar to either Pat and Patel or Harris and Harris. I would recommend getting both books if it's possible. If not, we're going to cover a lot of Harris and Harris and less so Pat and Patel. But Pat and Patel have a different approach than Harris and Harris. It doesn't cover digital design, for example. That's one downside with Pat and Patel. It doesn't cover digital design as much, I should say. So Harris and Harris will be more useful potentially for the labs as well because of the Verilog. So if you have to choose one, then pick Harris and Harris. But if you are able to, get both because both have different sorts of insights for sure. That's why I have both books. And in the end, as I said yesterday, this lecture really is not in any of the books outside. As you will see in the second half of the course, these books will not cover anything that we cover in the second half of the course. And we will not cover some things in these books also. Okay, so basically, let me tell you about the major goals of this course. I mean, I gave you some examples, but basically, we're going to cover in digital design and computer architecture. We would like to understand the basics, understand the principles of design, and understand the precedents, basically what came before. Because I think it's really important to understand what came before and understand the lessons that we have drawn from it so that we can actually do better in the future, right? And based on such understanding, we'll do a lot of things. First of all, we'll learn how a modern computer works underneath. We will evaluate trade-offs of different designs and ideas, and hopefully this will be exciting because I think the methodology we will apply implicitly or explicitly to these will be important for anything you do. In the end, the world is really about designs and ideas, and whatever you do in the future, you will be exposed to designs and ideas, and a methodical way of evaluating designs and ideas is going to be important. And then we're going to implement a principled design, a simple, very simple, unfortunately, microprocessor, because we don't have time in this course. If you had to implement a not so simple microprocessor, it'll take you a lot of time. And then we will learn to systematically debug increasingly complex systems. And this is going to happen in the labs for sure. You will have bugs. You will have issues with the platform. You will figure out how to solve them. Whatever bug you're having, it's important to keep in mind that whenever people design much more complicated processors and systems, they go through the pains of going through a bug for 10x or sometimes 100x the amount of time you put into it, which is interesting. So let me give you an anecdote over here. I was once at a conference. This is the DSN, Dependable Systems and Networks Conference in 2014. And there was a Google engineer who was giving a keynote speech. And this Google engineer said, we designed this beautiful software system. And then there was a bug one day. And we didn't understand what it was. So we chased this bug for 8 months, maybe 10 months. And then in the end, it turned out to be a bit flip in memory. So that's why he was invited to give this talk at the Dependable Systems Conference. And basically, sometimes the bug may come from actually bit flips in memory. And there's a beautiful description of that lecture if you can find it online. Okay, so and hopefully the bigger goal is to enable you to essentially be critical thinkers and develop new out-of-the-box designs. Of course, right immediately at the end of this lecture, you may not be able to do that, but I think that's as a teacher, an educator, that's my goal with every time I teach a class or mentor students. The goal really should be to enable you to be independent thinkers and independent developers who can make all of these design decisions and trade-offs to enable new things. Essentially, that's how progress happens, right? If you're limited to what happened from the past, then progress doesn't happen. Progress only happens with new ideas, new designs, and new creations in the end. And then, okay, the focus, as I mentioned earlier, is on basics, principles, and precedents, and how to use them to implement good designs. Okay, why do we use these goals? Clearly, one of the reasons is because you're here for a computer science or engineering degree, depending on where you're coming from. But I think more than that, regardless of your future directions, learning the principles of digital design and computer architecture, I believe, will be useful to do many things. So clearly, within the domain of computing, you can design better hardware. You can design better software because you know how the underlying hardware operates. You can design better systems by taking advantage of both hardware and software together. You can make better trade-offs in design in general, not just in computing. Understand why computers behave the way they do. And overall, more broadly, you can solve problems better. You can think in parallel. In fact, hardware is inherently parallel. You will figure that out in the Verilog assignments you will do. It's very different from the programs you have written in the past, unless you've done parallel programming. But for example, if you're programmed in C, Java, or Python, these are not parallel languages by nature, right? You have to do special things to make them parallel. And even then, they're not that parallel. Whereas Verilog is inherently parallel. Signals are generated concurrently. And you need to manage that concurrency if you really want to design hardware. So that's why designing hardware is actually a very good way of thinking in parallel. And I think critically, as I mentioned, that's going to be a very important goal of this course. And hopefully that'll be useful for many, many purposes. Okay, let me quickly go over some course info on logistics. I've already covered who I am. If you missed the last lecture, you can look at that last lecture to figure out who I am. But you can reach me here. Again, as I said earlier, my email tends to be not so reliable. I get too much email, unfortunately, and I cannot prevent it. And as a result, if you don't get an answer, don't take it as a no, or don't take it as a reason that I'm ignoring you. Either resend it, or better yet, I think it's better to CC some of the TAs also in the question, so that they can remind me if it's something that I have to respond to. Okay, I'm not going to talk about more of this, but I will introduce lecturers and PhD assistant. The head assistant is Juan. Maybe Juan can say hi quickly.
Hello, everyone.
Okay, that's Juan. Okay, yeah, you can see him also. That's good. And said is Hassan. Maybe Hassan can also say hi. Hassan is especially responsible for the labs.
Hello.
Okay, you can also see him. There you go. We also have Frank as a lecturer. We'll see how many times he lectures this time. Usually in the past, whenever I was out of town, he used to lecture. I guess the option of going out of town is not that much these days. So we'll see how we schedule with him. And then we also have other key assistants and guest lecturers. I'm just going to leave this over here so that you can see the names, but it'll take too much time to introduce everyone. But Jisung, Mohammed, Loiz, and Minesh are essentially key assistants and maybe sometimes guest lecturers also. Okay, there are also a bigger team of PhD assistants who are listed over here. I'm not going to mention their names, but you will get to meet them in office hours, in lab sessions, etc. And also we have student assistants who will be especially helpful in the lab sessions. Many of these student assistants are actually folks who have taken the courses in previous years and done well, excited about the topic. So they're actually going to help you with the labs. Some of them are not. Some of them actually are my master's students who know this topic really well also. So it's a good mixture over here. Some of them actually have been student assistants multiple years in a row, 3 or 4 years almost. Well, I don't know about 4 years, but 3 years, I believe. Okay, so there are some labs that are going to happen. You know the times, you can find them online, and we're going to assign lab assistants to these sessions. You'll be able to find them. And if you need help, please post to Piazza. And these are, Piazza is the major mode of communication for preferred or technical questions. And you can also write an email to this digital technique list. This goes to the instructor and all assistants. But I think technical questions are better handled in Piazza because you can also get an answer from some of your fellow students. And in the past, we've had nice discussions on Piazza between students. And I think I would prefer that because that enables you to learn more. That enables everyone in the class to learn more, as opposed to you trying to get an answer from TAs. And I think in the end, we vet the question. So if there's a good answer from some other student, we actually say, this is a good answer. And sometimes we actually correct the answers or give our own answers. So basically, Piazza is preferred, let's say, unless you have some logistics issues related to your own registration in the course, then you should definitely email as opposed to writing it on Piazza. I don't know if Piazza provides a method for that. If it does, then feel free to do it over there also. Okay, so come to office hours whenever you have questions, and we will provide Zoom links. So check the website for that. And this is the website. This is where you can get up-to-date course info. You can basically find everything related to the course over here. This is your single point of access. I would recommend frequently checking it. We, for example, have the YouTube live stream links updated. We put the lecture notes as early as possible, usually the previous night, but sometimes immediately before the lecture, depending on how overloaded we are. So basically, I would recommend using the website as a great resource. And sometimes you'll get emails. I think you may have gotten some of them. So please check your email. And also lecturers and teaching assistants will be people who you can get up-to-date info. So let me talk about some policies in terms of lectures. So lectures are, as you know, Thursdays, Fridays. So I mentioned that I will start a little bit early. I think it's better to start a little bit early and give you a longer break. So in the future, I will prefer to start about 14:05, between 14:05 and 14:10, let's say. I think that gives you enough time before the previous lecture. And these are all recorded anyway, so you can start live streaming later if you want to do it over YouTube. If you want to ask questions, I think Zoom is a better place, but YouTube is also fine. So it really depends on you. And attendance, again, I'm not requiring attendance from anyone, like any of my courses. I'm a big believer in students learning as opposed to being required to do things. So I think attendance, take it as something for your benefit. If you are benefit from the live lectures, and if you can ask questions, if you like the environment better that way, then attend it. I believe it's important, but again, I'm not going to require it. If you don't think you're losing much from attending live, then watch the lectures at your convenience. That's perfectly fine, right? And some days we may have guest lectures and exercise sessions. Next week, for example, we will talk about the labs. So I believe Hassan will give a lecture on how we will handle the labs. Okay, that brings me to labs over here. Next, see online, but you should definitely attend the lab sessions. These are mandatory because your progress in the labs really depends on your attendance, whereas that's not true for the lectures, for example. But of course, I wouldn't recommend delaying the attendance in all lectures to the end of the class. That's not a good way of making progress, right? It's good to pace yourself in a reasonable pace that you're comfortable with. But I don't think that pace should be, okay, I'm going to watch 25 lectures right before the exam. That's not going to work. And that's not a good mindset, I think. Okay, so you should definitely attend the lab sessions. Labs are actually about 30% of the grade. You can find the grading online. I think it was 30%. It used to be 25%. We increased it to 30%, which is the highest allowable by ETH. If it were up to me, I would actually increase it further because I think this hands-on experience plus homeworks are really important in your development, much more so than exams, in my opinion. But we're limited by the regulations over here. And unfortunately, that tends to be above my pay grade to change the regulations at this point. So basically, you're getting the maximum possible grade from the hands-on assignments. And that's essentially the reason why homeworks are also optional. We made them optional because we cannot assign grades to them. But I think we will talk about homeworks in a little bit. But as I said over here, labs will start March 9th. And you can find the handouts, etc., on the website. Okay, lab organization. I think you've gotten some emails related to this. You should definitely attend to them. These are key things. Choose your preferred group. As I mentioned yesterday, try to find a partner whom you know and whom you can work with. That's important. And I think some of you already mentioned that you're going to use your lab grades from previous years. And those of you who are going to use your lab grades, thank you. And I think that's going to be good for you because you're just going to get the same grade, which is probably perfect, given that you've, or close to perfect, let's say, given that you opted to do so. Okay, so let's talk about final exam. Unfortunately, there's a lot of emphasis on the final exam since it has to be at least 70% of the grade. It's a 3-hour written exam, and you can find examination rules in the course catalog. And also, we have all the previous exams on our course website. Exam questions are going to be sometimes similar to questions in optional homeworks and past exams, but that's not necessary. So optional homeworks are actually optional, but they're highly recommended, essentially. And I also say solving past exams could be helpful. And we're going to talk more about this toward the end of this course. We're going to actually have some discussion sessions that we're going to release where we go through the solutions to some questions. So again, certainly it will be important that you do well in the exam, but I would recommend that you don't worry about it too much and take this course as a learning experience overall, because I think what you're going to learn will be much more important. And again, in general, personally, I think that a single exam that's done at the end is not a great way of evaluating the learning and the potential of people. But that's what the regulations dictate today. If it were up to me, I would do something else, but that's we're bound by that, and you're bound by that. Basically, let me say that we're all in the same boat at this point. But I think we're going to help you as much as possible so that you can prepare for the exam. So you're going to see a lot of sessions. And if you really understand the material, I think by nature, you're going to do reasonably well on the exam. But again, that depends on how well of a test taker you are also, right? Some people just don't happen to do well on the exams. And we know all of that as lecturers. Okay, so these are some reading assignments for this week. As I mentioned, please do the reading assignments. You can start doing them. And we also have a supplementary lecture slides on binary numbers. I hope this is already up, but if not, the scribes will make sure that they're going to be up. And in the past, this used to be covered in lectures, but students found it way too basic. And I actually think that it's way too basic. So everybody learns about binary numbers, I believe, in high school these days. But if not, please go through the supplementary lecture slides. Okay, so these are some reading assignments for next week. Next week, we're going to cover combinational logic chapters from both books. And again, feel free to use either one. And check the course website for all future readings. There are going to be required, recommended, and mentioned readings based on the lectures. Again, required ones, nothing is required, I should say. but required ones are the ones that we believe that you should do to enhance your knowledge for sure. And if you don't do it, if you understand everything perfectly, no problem, I think. Recommended ones are definitely optional. So you can do it. You can enhance yourself even more. And mentioned ones are just mentioned. And feel free to do it if you have time, for sure. And I think it's also important that this course will be run similarly to how we ran it in the past. There's not going to be any fundamental change. There may be changes here and there. We may cover some concepts that we didn't cover before or take out some concepts. But we're going to be very similar to the schedule that we followed in spring 2020, which is last year. So you can basically anticipate and study future lectures and assignments based on that schedule. And everything is public. You can find the schedule, you can find the YouTube links, etc. And you can find the labs also. And this is a good example of last time prediction. We're going to cover prediction and speculative execution as a basic principle to design high performance processors in this lecture. And if you do what I just suggest over here, you would be essentially exercising speculative execution. Speculative execution is the general concept of doing something before knowing that it is needed. And it's a key concept we will cover in the design of microprocessors to improve performance. You can also improve your performance, right? You can actually watch all of these lectures beforehand, and you know what I'm talking about beforehand. I mean, at that point, you can either decide to watch my lecture this year or not. But usually I bring in some things into the lectures that is new. For example, we discussed Samsung's FIM DRAM, which was not in the lectures last year. Okay, so basically this is lecture 2A. It took a little bit longer than I expected. Any quick questions at this point? Okay, somebody asked, I think I should probably handle, why does this lecture have another name this year and not digital technique? So it's not just this year. Last year, it was also called digital design and computer architecture. So I think digital technique is an okay name also, but the lecture evolved to be, I think digital design by itself or digital circuits by itself doesn't do justice to the material that we cover. We don't just talk about digital circuits, we also talk about principles of computer architecture. In fact, we're equally balanced almost between digital design and computer architecture. That's why we renamed it, I think, in 2018 to maybe even 2019, one of those, to digital design and computer architecture to be much more accurate in its description. Okay, that's a good question. I like the critical thinking that some of you are doing. Okay, so I think right now it's a good time to very quickly take a break. We're going to take it. Okay, let me give a 10-minute break. We'll be back at 15:15, and we're going to continue with lecture 2B, which is going to be some mysteries in computer architecture. So we're going to have some more fun, basically, before we jump into the, let's say, true lab and digital circuits material next week. Okay, so have a good break for until 15:15. Okay, I think it's 15:15 now, and we can continue with lecture. Oh, lecture 2B. For that, I think I need to stop sharing and share the second lecture. Okay, that's good. Okay. Okay, I hope I have everyone back. Let's see. I think there was some discussion in the chat about whether you have to come to ETH for lab sessions. No, we will distribute the FPGAs. All of that information will be available online and next week when Hassan talks about the labs. Okay, so let's jump into the fun part of this today, let's say. Well, I guess the previous part was also fun. But now we're going to talk a little bit more about the mysteries that we briefly mentioned yesterday. And remember, yesterday we were talking about how do problems get solved by electrons. Just to jog your memory, I'm going to show this picture of the transformation hierarchy. We want to communicate a problem to be solved by electrons in modern technologies. And that needs to be described as an algorithm written in a programming language, executed on system software, and translated to an ISA, which gets implemented in the microarchitecture using logic gates and devices, essentially. And this was a narrow view of computer architecture, as we discussed, but we said that we're going to focus on the expanded view, even though a lot of this course will focus on the ISA, which is the hardware-software interface, microarchitecture, and logic. Okay, and you also remember that we talked about Richard Hamming, who mentioned that the purpose of computing is to gain insight. And we talked about this transformation hierarchy a little bit longer, but you can watch yesterday's lecture if you missed any of this. And we're clearly going to talk a lot more about ISA, microarchitecture, and digital logic circuits, which are building blocks of the microarchitecture. But just to jog your memory, ISA is the interface between the software and the hardware, and that's important. That is basically what the program assumes hardware will satisfy. Microarchitecture is the implementation of the ISA, and there may be many, many implementations of the same ISA. Like x86 ISA has many, many implementations, right? Probably many of you were not born when 386 or 286 were around. Right now, it's Intel, what is it, Skylake or something like that. They call it the core microarchitecture, but there's more. But basically, these are all implementations. AMD also has implementations, clearly. And then logic gates are, basically digital logic circuits are building blocks of the microarchitecture, for example, the gates. Okay, so somebody asked, is this person Hamming the person from the Hamming distance? And the answer is yes, basically. Richard Hamming, this is an aside. And I'd recommend taking a look at it. It's basically, it introduces the concept of Hamming distance as well as error detecting and correcting codes. And Hamming distance, if you don't know about it, clearly some of you know about it, but if you don't know about it, it's basically the number of locations. It's a metric to compare two equal length strings with. And essentially, the metric is defined as the number of locations in which the corresponding symbols of two equal length strings is different. So basically, if you have two strings, cat and dog, there are two equal length strings clearly in the alphabet, let's say English alphabet. And if you compare them, the Hamming distance is 3, right? Because every single character is different between those two, in each of the locations, right? Okay, basically Hamming distance is very useful for many things, and we may actually talk about it later on. But basically, in this work, Hamming developed a theory of codes that are used for error detection and correction, and these are still in use today in error correcting code circuitry in memories, for example, and other parts of the system. And I find some of the work Hamming did quite inspirational. Clearly, this work is very inspirational, but also he recorded a video. Well, it was not a video. It was a talk delivered, but it was also videotaped, I believe, on a number of occasions. But basically, he mentioned, he talked about how to do research, his principles of doing research in a talk delivered at Bell Labs, where he spent most of his career at. And I think this is a beautiful talk where you can get a lot of nice principles on how to do research, how to approach things, etc., how to learn new things in general. And I'd recommend looking into that. Regardless of whatever you do in the future, I think this could be useful in terms of learning and growth. It's a good mindset for growth, I would say. Okay, so if you revisit the levels of transformation, I think user is very important. And what we showed earlier did not incorporate the user. But user really interacts with many, many parts of the levels of transformation. Of course, the user is different. So some people have input problems. Some people design algorithms. Some people design programs and languages. Some people design runtime systems. Some people design ISAs or use ISAs. I should say design or use. And some people design microarchitecture and logic, right? So a user actually can be anyone who interacts over here. And perhaps the entire stack should be optimized for user. But then, of course, the question is, what does the user do and what does the user want? And it really depends over here. As I mentioned earlier, user enables the workloads also in computing systems. So it's important to understand the user. For example, if you really want to have a good programmable machine, maybe whenever you're designing the microarchitecture and the ISA, you should keep the user in mind also. Anyway, we're going to talk about some of these things later on, but we're going to focus especially on these parts of the stack as we discussed. Let me talk about why these levels of transformation exist. And basically a short keyword for this, or a short phrase of why they exist, is really the power of abstraction. Basically, these transformation levels create abstraction layers. And what is an abstraction? Basically, it's a higher level only needs to know about the interface to the lower level, and it doesn't need to know what's going on underneath, what is implemented. For example, whenever you're writing a program, you normally don't care about the operating system, right? Or the ISA, instruction set architecture, and certainly not the microarchitecture usually, because your program is independent. Your program gets translated to whatever is going to be executed at those layers. Okay, so a high-level language programmer does not need to know about the ISA or what the ISA is, because the compiler will take care of it, that translation, or how a computer executes instructions, right? Abstraction is great because it improves productivity, right? No need to worry about decisions made in underlying levels. So you can keep sane, let's say. For example, programming in Java is usually simpler than programming in C, which is usually simpler than programming in assembly, which is usually simpler than programming in binary, ones and zeros, which is usually simpler than programming by specifying control signals of each transistor or gate, let's say, every cycle. And we're going to do a lot of this in this course, basically, a lot of the lower level parts, assembly, binary, and control signals, as we talk about microprogramming, for example. But clearly, higher levels enable you the abstraction so that you don't need to think about what's going on in the lower levels. Then, of course, the question is, why would you ever want to know what goes on underneath or above? Of course, given that this is a computer science and engineering course aside, because if you claim that you're a computer scientist or engineer, in my opinion, you should really know how a computer works. Other than that fact, why would you want to know? Well, this brings us to crossing the abstraction layers. I think as long as everything goes well, actually not knowing what happens underneath is not a problem in general, I think. Because as everything is working well, right? As well as it could be, let's say, maybe I should put it that way. But usually it doesn't. Usually there are cases where your program runs slow, even though you said, okay, I did my best as far as my knowledge at this upper layer, and it's still running slow. Sometimes it doesn't run correctly. Sometimes it consumes too much energy, and this becomes a problem, especially in mobile systems, for example, or in the self-driving cars we mentioned yesterday. Sometimes your system shuts down and you have no idea why, and sometimes your system gets compromised and you have no idea how, even though your software is perfectly correct. We talked about meltdown and spectrum. We're going to talk a little bit more. Well, if you have these issues, then you may want to know what's going on underneath, or sometimes above also. Well, above is actually this part. What if the hardware you designed is hard to program? Well, maybe you want to know what's going on above you when you're designing hardware in this case, right? What if the hardware you designed is too slow because it doesn't provide the right primitives to the software, and software is actually spending a lot of time executing things that are just too slow, right? Whereas it needs some other primitives, some other instructions, like a systolic array-based multiply and accumulate, 64,000 of them, right? So basically, these are questions that you cannot easily answer if you don't know what's going on underneath or above you. If you're a software designer, you should know what's going on underneath. If you're a hardware designer, you should know what's going on above you. And also, sometimes you want to know everything. You want to design a much more efficient and higher performance system. Then you really want to know what your algorithm is, how it gets translated to your programming language, how it gets compiled, how it gets executed in hardware. And you want to really know how to co-optimize it. And that's what yesterday was about. Yesterday, we talked about these machine learning accelerators. They do all of that, essentially. And if they didn't do one of them, they would not be good enough. True for Tesla's self-driving computer, true for the in-memory processing system. You really need to co-design across the stack if you really want to have a much more efficient and higher performance system. But even if you're not co-designing across the stack, there's a lot of benefit to knowing what's going on underneath to solve the problems, regardless of wherever your core operating point is. Okay, so basically 2 main goals of this course, especially the second half after we built some basics, are first to understand how a processor works underneath the software layer and how decisions made in hardware affect the software or the programmer. So we're going to put as much emphasis as possible to this, like why some decisions lead to much faster programs. We will talk about that, much faster running programs. And what kind of programs should those be so that you can accelerate them? We're going to talk about that. And also, hopefully, this will enable you to be comfortable in making design decisions and optimization decisions that cross the boundaries of different layers and system components, because that is really where the innovation is going forward. And I think this is true for any cutting edge industry that is really using computing at the cutting edge. So if you're not bottlenecked by hardware and speed and efficiency, and also the cutting edge security issues, then probably you're not at the cutting edge. I will argue that. This is a bold argument, clearly, but I will argue that if you're okay with the speed of an existing computer, then you're probably not doing something cutting edge. I think this is a good thing to keep in mind, because it's always the applications that are straining the computers today are at the cutting edge. And I think that's a good way of also potentially a good litmus test of whether a country or a startup or a company is at the cutting edge. Okay, so let me now move into some example mysteries. I think this is going to be similar to what we discussed, actually. We're going to go into a little bit more detail, but I like doing this because this is really going to exercise what I showed you earlier. To solve these mysteries, you really need to know a little bit more about what's going on underneath or above you. Most of these are going to be underneath, essentially. So let's talk about them. And these are 4 mysteries that we're hopefully going to try to cover, hopefully all of them today, but unlikely all of them today. And we're going to talk about Meltdown and Spectre. We talked about yesterday. We're going to go into a little bit more detail, but again, I don't expect you to understand all of this, but I think I'm going to talk about it because it's very exciting and it's really important for you to be aware of. We're going to talk a little bit more about RowHammer today. We talked about it a little bit more than Meltdown and Spectre yesterday. And we're going to talk about a couple of issues related to memories, refresh, and memory performance attacks. I mean, I can easily also talk about some emerging applications, for example, genomics, but we already did talk about it yesterday. So I'm going to leave that for perhaps later lectures. And you can always find information, as I mentioned yesterday, in my talks. Okay, so let's jump into the first mystery, Meltdown and Spectre. A lot of you mentioned that you know about this. I don't know if you really know exactly how it works, but at least you know what these are. That's good. That means that these hardware security, microarchitectural hardware security vulnerabilities have had a huge impact in the field. Okay, so what are these? I already mentioned that these are attacks, microarchitectural attacks. They are exploiting vulnerabilities that are present at the microarchitectural level that leads someone to steal secret data from the system, even though everything seems to be good in the system. Meaning your program and data are perfectly correct. There are no bugs. Your hardware behaves according to the specification. There are no bugs. And there are no software vulnerabilities or bugs otherwise. And or also, I should put hardware bugs over here, essentially. Essentially, these are hardware security vulnerabilities that affect almost all computer chips that were manufactured in the past 2 decades. I should say high performance computer chips. Again, cutting edge computer chips. If a computer chip is not at the cutting edge, it can be low performance and it doesn't employ the things that lead to these issues. Now, you could argue that perhaps we should be reconsidering the design of computer chips that way. Yes, perhaps, but that comes at the expense of performance. Okay, so as I mentioned in the previous lecture today, is most high performance processors exploit speculative execution. It's a technique employed in modern processors to improve performance. And I mentioned that you could also employ speculative execution as humans. You could watch the last lectures from last year in this class so that you can get acquainted with the material much earlier. You can improve your performance that way, right? You could even solve the exams, etc., from last year. They're all open online. Basically, what you're doing is you're speculatively executing the lectures, meaning you're doing something before you know that it's needed. but you're maybe quite sure that it's needed, right? Because I told you, first of all. And second, if you look at the past history, the lectures don't change as much, even though there are new things that we discussed over time. So basically, we do it all the time in life also to save time and be faster, guess what will happen, and act based on that guess, right? Essentially, computers do that also. Processors, essentially to run programs fast, they guess what will happen. Instead of waiting for data or waiting for an instruction to complete, they execute the next instruction. And they execute the next instruction after that, and they execute the next instruction after that, before they know that these instructions will be executed. And actually, modern processors can go down maybe 200 or higher number of instructions that they execute before they know that these instructions are actually going to be needed or executed. Because they may not be executed actually because you may have a branch before them, meaning that your control flow will never get to that point. Okay, so basically modern processors speculatively execute code to improve performance. So this is one example code over here. It comes from banking potentially. It's made up, of course. I mean, it can happen. Anytime you make up some sort of code, interestingly, you find that there is some programmer that does some kind of code like this. Maybe not exactly like this, but kind of like this. So basically, if your account balance is less than 0, you do something. If it's less than 1 million francs, you do something else. Otherwise, you do something else. This may be the code your bank can be running on your accounts, right? For whatever reason, right? Maybe they're going to send advertisements to you, or maybe they're going to charge you accordingly based on your balance. Usually they charge you more if you have less in your accounts, which is always really weird to me, but that's how it happens. That's the state of the world, let's say. But basically, what the computer may do over here is account balance may take a long time to retrieve from memory or somewhere. Usually the memory access takes longer, as we discussed in the previous lecture. So the computer doesn't know which instruction to execute next, right? Because the instruction to execute next is dependent on the account balance and its value, right? So what the computer does so that it can be high performance is it guesses. It guesses that, oh, I should really go into this first part, do something over here. And that guesses basically this branch is going to go into this part. Account balance is less than 0. And it does this prediction based on some past information that is built into its structures. And we will talk about that when we talk about branch prediction lectures. We will talk about how existing computers predict which path in the program to take based on the previous instances where this branch went or where the other branches went in the program. So basically, the computers are guessers today. They're actually quite good guessers. Most of the time, they're correct. More than 95% of the time, they can guess the outcome of a branch well, because they've kind of seen the program in some way, seen this account in some way before, right? So, for example, the processor executes this do something over here, assuming that, guessing that the account balance is going to be less than 0. This improves performance clearly, especially if it takes a long time to access account balance. So, for example, account balance takes 200 cycles to retrieve from memory. And if you're fetching 1 instruction per cycle, you can execute 200 instructions before you know what the account balance is. And of course, we're going to talk about how to exactly do this later on. So don't worry if you don't understand how this is done. But this is done in existing processors. Existing processors are quite aggressive. So basically, they've executed, let's say, 200 instructions without knowing that those 200 executions will be executed. Now, if the guess is correct, great. Basically, they've saved a lot of time. Instead of waiting for the account balance to come back from memory, because it takes a long time to access it, they've done something useful, and their guess was correct. But if the guess is incorrect, then there's a problem. They have to ensure that none of the instructions that they executed should take effect, because that's wrong, right? They know that that's wrong at that point in time. And then they go back and execute the correct code. For example, if the account balance was actually not less than 0, but it was less than 1 million, they basically discard what they've done, 200 instructions over here or wherever it goes, and they redo. Well, redo is not the correct word, but they actually fetch the instructions that they're actually supposed to fetch, and they execute those instructions. So this is how speculative execution works. If you're correct, no problem, everything is fine. If you're incorrect, then you need to flush the instructions from the machine and execute the correct code. Okay? And this works perfectly. It's not a problem at all. There's no correctness problem here because the processors do it correctly.
So basically, speculative execution is invisible to the user. And we're going to talk about the difference between instruction set architecture and microarchitecture. ISA is in a contract between software and hardware. Programmer assumes what the hardware will satisfy. Programmer assumes sequential execution. Programmer doesn't assume speculative execution. Programmer doesn't know about this, essentially. Their assumption is that they've written code in sequential order. The processor is going to execute code in sequential order. Now, what the processor is doing underneath is it's implementing a microarchitecture. This ISA is implemented in such a way that instructions are executed in a different order than the programmer expects, but this different order is never exposed to the programmer. The programmer in the end sees the results in sequential order. And we're going to see exactly how this is done in real systems today. Now, Meltdown Inspector, so everything is correct, but Meltdown Inspector enables someone to steal secret data from the system, even though all of this is true. Why? Because it turns out speculative execution leaves some traces of secret data. So you execute these 200 instructions. Some of those 200 instructions access some things, and some of these things are not supposed to be accessed, let's say. I'm simplifying things a little bit because the real attack is a little bit more convoluted, let's say. But again, the purpose is not to talk about the real attack over here. But basically, you have some traces of secret data in the processor's cache, internal storage, and we're going to talk about cache also. Cache is locations that are recently accessed so that you can access them faster the next time. And the speculative execution of 200 instructions, as I mentioned, brings data that is not supposed to be brought or accessed if there was no speculative execution. Now, a malicious program can intelligently inspect the contents of the cache to infer secret data that's not supposed to access. And again, I'm not going into the details of how this is done. And a more intelligent malicious program can actually force another program to speculatively execute code that leaves traces of secret data in the cache. So this is even more advanced. And you need to really know how the microarchitecture operates to enable these attacks. So essentially, what Meltdown Inspector do is processor cache is a side channel. Side channel is essentially a channel through which someone sophisticated can extract information. It's not a direct channel. Direct channel means you expose this information to someone knowingly. Side channels, you expose this information from someone unknowingly. And someone can actually take advantage of this information for their benefit, even though the information was exposed unknowingly. So basically, speculative execution leaves traces of data in the processor cache, meaning this is not a problem architecturally. ISA doesn't say anything about this. Architecturally, this is correct behavior with respect to specification, but this leads to a side channel through which someone sophisticated can extract information. In this case, processor cache leaks information by storing speculatively accessed data, and a clever attacker can probe the cache and infer the secret data values by measuring how long it takes to access the data. So this is where actually things become a little bit more complicated, because you don't access the secret data directly. You really access something that enables you to infer the value of the secret data. And the way you enable, you infer this is really by measuring how long it takes to access the data. Okay. So a clever attacker can force a program to speculatively execute code and leave traces of secret data in the cache. So this is a sophisticated attack. It's not an easy attack. RowHammer is much easier actually compared to this, I will say. And this was reported by Google Project Zero, Jan Horn. You can read this. There are also other papers. I see some comments. Can we just flood this channel where traces of secret data are being left with junk after we're done, or like erase the data? So potentially, yes, they could be part of the solution, but they create side channels on their own. So if you erase the data, that creates some other side channel potentially, because now you're erasing some data that's expected to be in the cache. So you should be really careful. Side channels are a bit dangerous. And also you need to handle them carefully. Whenever you're fixing one side channel problem, you should not create another side channel problem. Okay, so maybe someone is, so it's good that you guys are thinking creatively, let's say. Just create a keyword which tells the program to specifically never preload a part of code before used. So this is actually great, because this is one of the solutions that were employed by Intel, I believe. Intel suggested, actually, they provided compiler patches where you could insert some instruction whose name right now escapes me. All these instructions are named really oddly, but you could insert some instruction that basically disabled speculative execution for some parts of the code. And you need to insert those instructions very carefully, of course, whenever you're accessing some secret data that's supposed to be important. Of course, this requires modifications to your program, modifications to your compiler, etc. But this could be part of your solution. The downside is it comes at a performance cost, of course. But I think I like the thinking that you are having over here. Essentially, you can have that sort of instruction that can disable speculation. And that was one of the proposed solutions to this problem. But later, people figured out that sometimes it's hard to insert those instructions. You don't know whether you should insert those instructions here or there. Basically, you need to really patch every single program with those instructions somehow. And that may not be necessarily an easy task. Okay, so there are 3 questions I have over here. And I think the answers will be kind of obvious. These are leading questions, more rhetorical questions, let's say. Can you figure out why someone stole your secret data if you do not know how the processor executes a program? And I will argue that the answer is no. You're clueless, basically. If you have no idea how your microarchitecture is executed programs and someone steals your data this way, you're clueless. And you may be actually leaking a lot of information. You may be a bank who said, I don't care about microarchitecture. I just buy processors from Intel and AMD and ARM, and I'm a happy camper. And in the end, everybody may be stealing your secret data. Okay, of course, I'm exaggerating, but that's, I think, an innovation agnostic mindset that sometimes companies may have. So basically, you need to know what's going on underneath here. Can you fix the problem without knowing what is happening underneath, i.e. inside the microarchitecture? And again, I will say the answer is no. And again, you may say, okay, it's not my problem, it's Intel's problem. I will argue that it's your problem because in the end, it's a security problem. And in the end, manufacturer may say, okay, I fixed the problem, but how do you trust that, right? If you really care about the security and privacy of yourself and your clients, you should really somehow have ways of really verifying the issue on your own. And the only way you can do that is by knowing what's going on underneath. Okay. And can you fix the problem well or fundamentally without knowing both software and hardware design? And again, the answer to that is no, I believe. So it's great that you guys are actually coming up with some suggestions over here. And this is exactly what I would like to see in this course. And that's why I actually talk about these mysteries. But basically, these suggestions are good starting points. But in order to actually enable, to be able to make the system secure, you need to actually think a lot more to enable these ideas. So you have good ideas potentially, but you need to enable these ideas somehow. Okay. And then, okay, I have 4 questions. I said 3 in the slide, but 4th one's coming. Can you construct this attack or similar attacks without knowing what's happening underneath? And that's an absolutely no. Basically, the folks who construct these attacks learned a whole lot about microarchitecture. In fact, people who worked on this worked a lot on RowHammer, and they got excited about microarchitecture quite a bit. And they actually developed these attacks by really understanding what's going on truly in modern microarchitectures today. Okay, so there are other questions also. What are the causes of meltdown and Spectre? Again, I'm not going to go into the details of this. I give you a high level. Hopefully, after this course, you'll have a good idea of understanding why these happen. Maybe you can actually run some of those meltdown and Spectre codes and do the attack yourselves. How can we prevent them while keeping the performance benefits of speculative execution? So how can we prevent them? Maybe easy, as long as you're careful. But of course, how do you keep security while also keeping performance is also very important. So it's very difficult to actually keep security and performance at the same time. So someone is asking the question, do the programs leave the trace anywhere apart from the processor cache? And the answer is yes, basically. There could be other places, actually. And there are other works that built on Meltdown and Spectre that show that you could get side channels on other parts of the system, like the load store queue or different parts of an instruction, a microarchitecture. So that's a very good question. I think this is also critical thinking. Now that this happened, can you do it in other parts? Right. Of course, basically, do you do software changes, operating system changes, instruction set architecture changes, microarchitecture or hardware changes, change at multiple layers done cooperatively? Many, many potential choices. And these are actually research questions right now people are working on. Then, of course, the last question is, how do you design high-performance processors that do not leak information via side channels? And this is still a research question that's an ongoing topic of investigation. I don't expect you to answer these questions clearly, but the fundamentals we provide in this course are really at the heart of you understanding what's going on and answering these questions. So by the end of this course, I would hope that most of you have a good enough understanding of what a microarchitecture is, that you can actually intelligently answer a good chunk of these questions. And maybe, who knows, develop some solutions also. Okay, so basically, Meltdown and Spectre span across the hierarchy, in my opinion. Some of the solutions can be programming solutions, for example, as one of you mentioned, that gets compiled by the compiler. So we really need to look at the solution space from algorithms to logic. And if we just look at the computer architecture, take the narrow view, I don't think the solution, we're basically restricting the solution space. And the takeaway over here is, I think, breaking the abstraction layers between components and transformation hierarchy levels and knowing what is underneath enables you to understand and solve problems. And this is a critical problem for hardware security. There are many, many more papers that were written after Meltdown and Spectre papers that show that there are other vulnerabilities that are of similar nature. And basically, the problem goes on. Let me put it that way. There are also other work that show that power can become a side channel. So, for example, when you're executing different instructions, you consume different amounts of power. And whenever you're actually operating using different values, you're executing different amounts of power. By doing statistical analyses on the power consumption of your processor, you can infer what values are being used by the instructions. And if those values correspond to a secret key, for example, that is used in a cryptographic protocol, then you can actually potentially get that secret key that no one else other than the person who really put it there was supposed to know. So you can see that there are many other potential side channels that can happen in an existing system. And security is really an exciting topic today. Okay, I think there are some other solutions that are proposed. I'll let you guys think about it. But basically, if you move the data somewhere else, you're actually creating another potential side channel also, and it could also be slow, right? As one of you mentioned. Okay, but it's good that you guys are thinking. That's always good. Okay, basically, clearly, you can understand and solve the problem, but you can also understand and critique cartoons as well. So this is a cartoon from XKCD. I'm not going to go through this. You can actually go through this on your own whenever you want. It basically talks about this Meltdown and Spectre, blah, 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 blah. I'm not going to also interpret it. I like this cartoon. It's a bit cryptic, but I like this part also, basically. It basically talks about Meltdown and Spectre and speculative execution and what's that. And then this girl over there says, honestly, I've been assuming we were doomed ever since I learned about RowHammer. And that's probably true. That's kind of a good interpretation of how the events unfolded over time. Okay, before I move to RowHammer, based on that cartoon, let me put this important note. Basically, design goal of a system determines the design mindset and evaluation metrics. So Meltdown and Spectre are there because the design goal never thought about security. And rightly so, I think, because security was not that important. And the drive was always for high performance for some time. Because the design goal of cutting-edge processors employed everywhere in our lives has mainly been focused on high performance and low energy relatively recently. Of course, cost is always there. Even energy is relatively recent. It happened starting in late 1990s, early 2000s. But it does not include security or information leakage as an important constraint. So going forward, incorporating security as a first-class constraint and a metric into design and education is critical in today's world, and especially hardware design, but also in software design. I think software courses usually don't pay attention to this as much, but that's exactly why we're starting with this in this course, because I think this needs to be incorporated into the mindset of students like you going into the future so that we can solve these problems in a better way. Of course, the solutions should not come at the expense of huge performance losses, in my opinion. So basically, this is the design mindset. These folks are constructing New York after the World War, and they're happy right now. But if there's a security attack on the road they're sitting, they will not be happy in the next minute, right? I will argue that a good mindset is thinking of security as preventing unforeseen consequences in the system. This is a very broad definition of security, in my opinion, but I like this definition because whenever you're a designer, security is a critical issue. And increasingly, we're going to rely on a hardware that's going to determine the future of our lives, artificial intelligence, self-driving cars, whatever, things that are making decisions for our health, for genome analysis and more, helping the doctors. And if we have security problems, then we'll have huge issues over here. Brain-computer interfaces, things like things that we put on our heads so that we can have virtual reality. If these are subject to these security attacks, then we have a huge problem, right? It's good to have the design mindset such that even if there are unforeseen consequences, we should be able to prevent them such that we can quickly patch the hardware, for example, somehow. Okay. Okay, so there are two other goals of this course. And as I mentioned earlier, I'd like to enable you to think critically and to think broadly. Think critically means you should really be thinking critical about every aspect of what we've discussed. And I think that's really the biggest learning, in my opinion. If you're able to think critically and broadly, and this helps you in the rest of your life, then I think this course has been successful. I think the exam score means much less to me than these skills that you will learn that will benefit you for the rest of your life. So if you would like to learn and discover further, I mean, this is a bit outdated information, but these videos provide the Red Hat video as a high-level information, and there's a more comprehensive explanation that you may not be able to understand with your current background, depending on what your background is over here. But again, reading the papers could help you as well, clearly. I would suggest keeping on attending lectures and taking in all the material. And feel free to talk with myself in the future and also other TAs. I have many bachelor's and master's projects on hardware security, for example, and fundamentally secure, safe, and reliable computing architecture is a key direction in scientific investigation and design today. Okay, so let me jump into RowHammer. There's one question I will quickly take. Does this attack also leave traces of who did the attack as well, or is it untraceable? So once someone gets the information, so I don't know the answer to this question perfectly, I think. I believe it could be untraceable if the attacker is knowing what they're doing. So hopefully that's a satisfactory answer. And usually the attackers are actually quite clever. Okay, so let me jump into RowHammer. We don't have a whole lot of time, but I would like to finish RowHammer today. I'm going to go relatively quickly because we talked a lot about RowHammer yesterday. But I think this is a really fundamental mystery also, as you showed, as you also saw in the XKCD cartoon, right? Because this is one of the first hardware security vulnerabilities that really made a huge impact in the software world, I should say, because the software world really embraced RowHammer, and they basically figured out many attacks on how to exploit that bit flip. And you know from yesterday that this issue is still not resolved. Okay, very quickly, as I said yesterday, this is the fact that you can predictably induce bit flips in commodity DRAM chips. And when we first did the studies starting in 2012, we found out that more than 80% of the tested DRAM chips are vulnerable to this problem. And it's really the first example of how a simple hardware failure mechanism, a circuit level failure mechanism, can create a widespread system security vulnerability. And as a result, you see articles that look like this. Forget software, now hackers are exploiting physics, which is a good explanation of RowHammer. As I explained yesterday, RowHammer is all about disturbance, meaning whenever you access a row, activate a row, you're disturbing the rows physically adjacent to this row. So you keep on activating, applying high voltage to this word line, closing, applying low voltage, again, apply high voltage, low voltage, high voltage, low voltage, high voltage, low voltage, high voltage, low voltage. Basically, you're really swinging the voltage on this word line, and you're really disturbing the cells that are around you because of this voltage effects that you're causing. And I'm going to go into a little bit more detail over here, but we're not going to go into the exact circuit level details. Somebody says, does RowHammer need a physical access? No, absolutely not. You don't need physical access, as we will also see. You can launch these attacks in software, purely software, in fact, from remote computers. But basically, vulnerable cells, bits in adjacent rows can lead to bit flips. We call this the hammered row. We call this victim rows. As I said yesterday, we found out that most DRAM chips in the field are vulnerable, more than 80% from all three major manufacturers, as we discussed. And this is a scaling problem. The chips that we tested that were manufactured before 2010 did not have any errors, as you can see on the y-axis, but the first errors happened in chips that were manufactured in 2010. And the chips that were manufactured between 2010 and 2012 and 2013 were all vulnerable. And our attack is not the best attack at the time, because this is the first attack. Later, people built on our attacks and built better ways of doing RowHammer, so they increased the error rate significantly. Okay, so why is this happening? Because DRAM cells are just too close to each other. They're very small. They're becoming smaller, and they're also too close to each other. As a result, they're not electrically isolated from each other. Access to one cell affects the value in nearby cells due to electrical interference between the cells and wires used for accessing the cells. And we're going to see the cells and wires used for accessing the cells later on when we talk about memory, for example. This is also called cell-to-cell coupling or interference. An example is when we activate or apply high voltage to a row, an adjacent row gets slightly activated as well. And vulnerable cells in that slightly activated row lose a little bit of charge. And if RowHammer happens enough times, thousands of times, charge in such cells gets drained. As a result, before you had charge, now you don't have charge. Charge means encoding as 1, for example. Now your encoding goes to 0. So a bit flip happens because your cell is now interpreted as a 0, whereas originally it was a 1. And this is clearly bad, right, as we discussed yesterday. So as a result, the simple circuit level failure mechanism has enormous implications on upper layers of the transformation hierarchy, because the bit flip directly gets exposed to data structures in your program or system structures. So let me give you the code that we developed in 2012 to do this attack. This is basically a 6-line x86 assembly code. If you know x86 assembly, you will see that. But we're going to learn MIPS assembly, which is very similar in some level. Basically, what this code does is it selects addresses X and Y such that they map to the same bank in DRAM. Don't worry if you don't know what the bank is. We will see that. But they're close enough to each other, basically, in some structure. And then what it does is it basically bypasses the cache. Again, don't worry if you don't know what a cache is. We will learn about this. Bypasses the row buffer. We will also learn about this later on. To ensure that you're basically doing this. Ping-ponging activates to rows X and Y over and 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 over enough times before the cells get refreshed. So DRAM gets refreshed once in a while. We will talk about that. So refresh happens so that you can replenish the charge in the cells. But if you can do enough activates to induce these bit flips before the cells get refreshed, you get errors that look like this. And this is our program. You can see that we put it on GitHub. Later, Google improved it and other folks improved it. So this is actually an obsolete program right now, but you can still potentially download your program and run it on your computer. I'd recommend downloading Google's program, which builds on this one, and seeing if you're vulnerable to RowHammer. It's a good thing to test, I think. Okay, so basically, these are the errors we observed at the time we wrote the paper. Intel and AMD systems are both vulnerable, as you can see. I'm not going to go through the details. You can read the paper. And as I mentioned yesterday, we said that this should not happen, basically. If this is happening, someone can hijack your system. Because an access to one memory address now has unintended side effects on data stored in other addresses, and someone can actually use these unintended side effects for their benefit, so that they can actually gain access to your system. And these good folks from Google Project Zero showed exactly that. Basically, a year later, after our study, this is a copy paste from their blog post, which you can find in this link over here. A year after our study, they basically said they learned about the problem from our paper. They test the selection of the laptops and replicated the RowHammer problem, basically. It's always good if someone else independently, completely independently of you, replicates the problem clearly. And they basically built 2 attacks. One attack is very interesting. It basically uses these bit flips to gain kernel privileges on x86-64 Linux when you run this process as an unprivileged user level process. So what it does at a high level, I'm not going to go into the details because this is beautiful security engineering over here. And if you're really interested in system security and computer architecture and security engineering, you should really look at this blog post. So basically, when they ran this program on the vulnerable machine, it was able to induce bit flips and page table entries on its own. So page table entries provide protection for the program. It decides whether a program can access this part of memory or cannot access this part of memory. And if you can actually modify these page table entries, you can basically enable access for yourself to any location in memory. Clearly, normal programs should not be able to modify the page table entries and change their own permissions. This is a function of the system. But if you know what you're doing, you can induce these RowHammer bit flips in locations in your own page table, and then flip the right bit such that you can get right access, right permissions to locations that you really want. Meaning you can become a root, basically, and gain kernel privileges. Okay, so I'm not going to go through the details. This is beautiful, I think. And later, this became famous, as we mentioned, and hackers have a nice ways of putting what RowHammer is in these beautiful analogies that I'm not going to talk about again. You can learn a lot more about RowHammer in the reference that I will mention. And later, this kind of exploded, and people actually showed that they can gain unrestricted access to systems of website visitors remotely using JavaScript. So basically, they're launching these attacks on a remote machine, as you can see. And then these folks showed that you could do this on a cell phone. If you download their app, for example, that app can take over your private data on your cell phone or take over your cell phone by hammering and gaining access to locations that they're not supposed to gain access to. And I think they still have the program on Android. If you have an Android phone, you can test. Other folks show that you could do this using GPUs. We're going to cover GPUs later in this course. So you're going to actually learn a lot about these concepts that enable you to do these attacks and prevent these attacks later on. Other folks showed that you can actually do these attacks by over the network using an interface called remote direct memory access. This is an interface through which you can do remote programming such that you can actually collaborate between multiple computers, but you can now induce bit flips in some remote computer. And these folks actually showed exactly the same thing. And these folks show that you can leak private data even if you don't gain access to the computer. And these folks, as I mentioned yesterday, these two folks, sets of folks, I should say, show that they can basically render deep neural networks completely ineffective by doing these bit flips, RowHammer bit flips. They can basically get rid of the accuracy from 90% to 10%. And I think this is very dangerous, clearly. If we're going to rely on deep neural networks to do our vision in self-driving cars, we'd better be sure that somebody is not launching a RowHammer attack on that car. Because it takes only one RowHammer attack to succeed, right? Especially these deep neural networks are easier, in my opinion, to actually disturb because reducing the accuracy is easier, in my opinion, again, than taking over a system completely. You don't need to take over a system completely in this case. You just need to reduce the accuracy to a level that you cause problems. And that's not hard to do, in my opinion. Okay, so that's why I think that's one of the other reasons why hardware is extremely important today. And again, if you encounter people who say, oh, I don't care about this, it's the DRAM manufacturer's problem, maybe you should ask them to think more critically. Okay, so maybe this is another security implication, right? After all of this, you say, oh, my computer is not working, I'm going to get rid of it, but I don't think that's a good solution. So this is our infrastructure where we did a lot of the RowHammer experiments. These are FPGA-based infrastructures. In this course, you're actually going to use FPGAs, as we discussed earlier. Let me quickly talk about how to fix this problem. I'm going to finish the RowHammer. Unfortunately, we're going to take a little bit longer. Sorry about that. Again, you can watch the rest of this lecture. But again, I think if you need to go, that's perfectly fine also. But if you're interested in staying, feel free to stay. Hopefully it'll be interesting. So there are basically a bunch of potential solutions to this problem. Making better DRAM chips is not easy. Refreshing frequently could solve this problem. Actually, that was actually done by industry. But this is bad, actually, as we will see tomorrow, not tomorrow, next week, because refreshing frequently leads to a lot of power and performance impact. Adding error correcting codes, sophisticated ones, can potentially solve the problem, but it's extremely costly, actually. I wouldn't recommend it. Keeping track of some access counters and intelligently figuring out whether you're actually doing seeing RowHammer or not. I think there's some cost issues, but I'm not closing this door over here. There may be a good solution space over here. So clearly making better DRAM chips involves isolating things better. This is costly unless someone finds a really great way, cost-efficient way of doing that. But I think the second and third solutions are not good solutions, I would argue. The first solution may be good depending on what people find. It's a very hard find. The last solution may be good depending on what people develop. So basically, we still can be creative in the space. But I think we kind of dismissed these solutions initially because we have a better solution, as we will discuss in a little bit. So industry solved this problem by increasing the refresh rates. This is Apple's security patch. As you can see, they said a disturbance error, also known as RowHammer, exists in some DDR RAM that have led to memory corruption. This issue was mitigated by increasing memory refresh rates. They didn't tell exactly how much, but I believe it's about 2x. This means that your memory is doing 2x refresh right now, which is bad because it's consuming power. So the cell phone is consuming power even when it's turned off right now, basically. And Apple was nice enough to give credit to our work and Google's work over here. As you can see, they referenced the original paper that led to all of this. Okay, so everyone else actually released similar patches. So refreshing frequently reduces the problem probability because now you can actually do fewer activates before the cells get replenished in their charge. Okay, our solution is simpler. Very quickly, it's so simple that I think you'll be able to appreciate it. But basically, it's probabilistic. With very little probability, after you close a row, we activate the adjacent rows. This means that we refresh the adjacent rows with very low probability, just the adjacent rows. And the probability is very little, as you can see over here, 5 out of 1,000 times. And if you're paranoid, you can increase that probability, of course. And this gives you a great reliability guarantee. Of course, an attacker can still potentially be try to attack, but I haven't seen an attack that overcomes this yet. Usually people say probabilistic solutions do not work, but I haven't seen an attack that actually attacks a good probability level at this point. Okay, and this solution, a variant of the solution, was actually implemented by Intel as part of their probabilistic TRR mechanism at the BIOS level. So you could actually, you used to be able to pick your solution in RowHammer. You could easily either increase your refresh rate or pick this probabilistic RowHammer protection, which is similar to what we have proposed, except at the BIOS level as opposed to seamlessly to the programmer or the user. But again, that's fine. I think this was a reasonable solution. This could have been developed even more. But unfortunately, at some point, what happened was DRAM manufacturers said, okay, we solved the problem, it's secure. And then Intel disabled the solution in their memory controllers. But it turns out, as I discussed yesterday, the problem was not solved, right? Okay, so let me give you some thoughts. This is a simple hardware failure mechanism that can create a widespread system security vulnerability. How to find, exploit, and fix the vulnerability requires a strong understanding across the transformation layers and a strong understanding of the tools available to you. Fixing needs to happen for two types of chips, existing chips that are already in the field, and refresh is the best solution, perhaps, increasing the refresh rate. But future chips have a lot more potential, like probabilistic adjacent row activation, like I talked about. And mechanisms for fixing are different between the two types, as we discussed. So let me give you some aside. I wanted to enhance your knowledge a little bit. Maybe some of you have taken some distributed systems course. You're going to take some distributed system course. But this class of failures is known as Byzantine failures. And Byzantine failures are characterized by undetected errors, essentially. It's opposite of a really good principled way of designing dependable systems. Fail fast. If you have a failure, you either fail with an error, don't continue, or don't give any results. This is a really great principle for designing dependable computing architectures. But RowHammer violates this right. Clearly, you get undetected bit flips. And erroneous can be used for malicious. Intent is the only distinction, basically. So basically, it could be a reliability problem, it could be a safety problem, and it could be a security problem, and because somebody malicious can take advantage of that bit flip. And it turns out it's very difficult to detect and confine Byzantine failures. Do all you can to avoid them. And this is first discussed in the Byzantine generals problem. Actually, this slide I borrow from Satya, who teaches distributed systems at Carnegie Mellon, who is a former colleague of mine. This is an undergraduate class in distributed systems taught at Carnegie Mellon. And when he heard about RowHammer, he immediately incorporated RowHammer into his distributed systems course, saying that, okay, this is an example of a Byzantine failure, and we should really do all we can to avoid this. Okay, if you're interested in this, there's a lot of really interesting theory of distributed systems, actually. Byzantine generals problem. Actually, I will read this paragraph to you because I think this is really important for education. Basically, this is a seminal paper written by Leslie Lamport, who won the Turing Award for his work in distributed systems and multiprocessors. And he introduced the Byzantine generals problem. And the idea is, let me read it. Reliable computer systems must handle malfunctioning components that give conflicting information to different parts of the system. A bit flip is conflicting information, or it can lead to conflicting information. This situation can be expressed abstractly in terms of a group of generals of the Byzantine army camped with their troops around an enemy city. Communicating only by messenger, the generals must agree upon a common battle plan. However, one or more of them may be traitors who will try to confuse the others. The problem is to find an algorithm to ensure that the loyal generals will reach agreement. It is shown that using only oral messages, this problem is solvable if and only if more than 2/3 of the generals are loyal. So a single traitor can confound two loyal generals. With unforgeable written messages, the problem is solvable for any number of generals and possible traitors. Applications of the solutions to reliable computer systems are then discussed. I find this a very beautiful paper. I'm not going to go into more details of this Byzantine failures. Byzantine failure is basically something that breaks the assumptions in this paper. Okay, so if you're really interested in RowHammer, there's a lot you can now reference. Basically, we have source code. This was our source code. Google's source code is on their website, on GitHub also. This was the paper that we wrote 7 years ago. This is a more recent paper, a retrospective paper that we were invited to write. It doesn't cover what happened in 2020. But let me finish with some takeaway, and I'll give you more resources, and then we're going to conclude. But basically, RowHammer is another example of how breaking the abstraction layers between the components and transformation hierarchy levels and knowing what is underneath, what goes on underneath, enables you to understand what's going on and solve the problems, potentially attack the systems and also create new solutions. And as I said yesterday, RowHammer is still an open problem. Basically, DRAM manufacturers said they'd solve the problem, and some of the industry trusted it. And even Intel, as I mentioned, that because DRAM manufacturers said, oh, we have a solution to the problem, Intel took off their, in my opinion, potentially better solution to the problem. They actually disabled that solution. But the problem did not go away, essentially. The problem was not solved. So basically, this work shows that the problem is getting much worse. You can actually induce bit flips with much smaller number of activates. This work shows that DRAM manufacturers did not really solve the problem. An intelligent attacker can bypass the solutions with intelligent reverse engineering. By just doing just enough reverse engineering, you can show that you can induce RowHammer bit flips in in chips that are claimed to be protected against RowHammer perfectly, and then you can take over the system in those chips. Okay, and then you can also look at this paper if you're interested. And next week, we're going to present another solution to RowHammer that is based on the access counter based solution, I will say. This is a low-cost solution, maybe not as low cost as what we discussed, probabilistic adjacent row activation, but I think it's good to investigate solutions going into the future. And if you're interested, again, we're not going to talk about RowHammer anymore in this course. We may mention it once or twice when we talk about memory, for example, or memory controllers, or something that inspires us to talk about it. But if you're really interested about the story of RowHammer, you can read more, listen to this lecture that goes into a lot more depth. And again, we talk more about it in the computer architecture class. Okay, so that brings us to the end of RowHammer. I guess before we conclude, maybe I will quickly mention this. So basically, we're talking about reliability and security, right? And reliability and security and safety are really at the bottom of the hierarchy of needs. This is Human Hierarchy of Needs by Abraham Maslow, who is a famous American psychologist who essentially dedicated his life to understanding why humans do the things they do. And in the end, because of his dedication. So I think of like Maslow as a person who is very similar to Calatrava or Frank Lloyd Wright. Basically, these people are extremely hard workers with a lot of insight to the problem and principled thinkers. And in the end, they had a lot of impact on their respective fields. And Maslow had this impact. He's much more known for this hierarchy of needs of humans, which is used essentially in economics, psychology, organizational psychology, politics, etc. And basically, that's where he said that first we need to have our physiological and safety and security needs are satisfied before we can think about bigger things. And that's true for computers also, I think. We really need to start with reliability, safety, and security and ensure that computers work. Otherwise, if they're vulnerable to something, we may actually have a self-driving car that keeps crashing once in a while and with bad consequences. I mean, that's one example. That's only one example, right? There could be thousands or millions of examples. So I like this hierarchy of needs, and it applies to computers also. So I'm going to mention this later on as well. So I also use this analogy when I talk about security. This is a bridge that used to be on Tacoma Narrows in the Washington state where I used to live in, very close to Seattle. I was at Microsoft Research, where I started the computer architecture group over there. And I used to cross the Tacoma Narrows, but after I didn't cross this bridge because this bridge had a failure in it. It had a bit flip in it, and it basically broke down one day, 6 months after it was built in 1940. And this is taught in civil engineering classes right now as how not to build bridges today. But basically, I think of this as a bit flip, and this is critical infrastructure. It's unfortunate, and bridges are critical infrastructure. Humans have been building bridges for thousands of years, right? And clearly they're critical infrastructure, right? If you have a bit flip on a bridge like this, and if there are lots of cars, then you will have problems, right? You will have safety problems, you'll have security problems, and clearly it's a reliability problem. Now, think about how important this bridge problem is compared to having this sort of security problems, like RowHammer sort of security problems in the massive number of computing devices that we employ in our lives everywhere. I would argue that this bridge is not that important. So the bigger problem really exists in computing devices. And if we actually don't design our computing devices in a safe, reliable, and secure manner, in a robust manner, in a way we can depend our lives on them completely, then we will have much bigger problems than what is depicted in front of you in this picture over here. That's why we start with safety, security, and reliability. And that's why I showed this picture also, because this picture, I think, is an example of how we are treating our computing systems today. In fact, our computing systems are probably much less reliable than the rod these workers are sitting on at this point. Our computing systems are much more vulnerable. And I think we need to have a change of mindset, think about security as a way of preventing unforeseen consequences going into the future. Wow, I still have more slides, but let me quickly conclude the rest of it also. But basically, RowHammer has enabled that mindset, in my opinion. A new renewed interest in hardware security attack research. Real memory chips are vulnerable in a simple and widespread manner. This causes real security problems. Hardware reliability to security connection is now mainstream discourse in real. So software engineers at some point never really cared about hardware reliability. But after RowHammer, there were a lot of security engineers who really started caring about hardware, which is really, really interesting. And now there are many new RowHammer attacks. There are tens of papers in top security venues. In fact, some of the papers we cover in our seminar class, there's more to come as RowHammer is getting worse. There are many new RowHammer solutions. I mentioned some of them. Some of them are for real products, as you can see. Many solutions proposed in top venues. This is incorrect. It's coming up in 2021, as you can see. And principled system DRAM co-design is actually a good solution direction. But I think there are many more to come. And also, perhaps more importantly, RowHammer has enabled a shift of mindset in mainstream security researchers. General purpose hardware is fallible in a very widespread manner. Its problems are exploitable. And this mindset has enabled many system security researchers to examine hardware in more depth and understand how hardware works internally and create or find vulnerabilities in hardware. So I think it's no coincidence that two of the groups that discovered Meltdown and Spectre concurrently heavily worked on RowHammer attacks before. And I think there are many, many more attacks to come. In fact, we've seen it. This slide I prepared actually 2 or 3 years ago. I think it was 3 years ago I prepared the slide. And since I wrote the slide, all of these more to comes have been correct. So basically, I predicted the future correctly. There were more RowHammer attacks. There were more RowHammer solutions. And there were more microarchitectural attacks inspired by Meltdown and Spectre, and which were inspired by RowHammer before. Okay, so for more RowHammer, basically take a look at everything else that I mentioned. This is just one of those things that doesn't cover the new work as we discussed. Okay, so we took a bit longer than expected, but again, this was all optional in a sense. This is a point where I will, I think, conclude, and I will take any questions, any quick questions in the next 1 or 2 minutes. If there are some quick questions, let me know. Anyone? So I think somebody on YouTube said there have been airplanes that have had screws come off because they vibrate at the same frequency with the running engine. So that has also happened actually. I recently seen a picture of an airplane whose engine is burning, and airplane still continues flying because they actually had good design principles, because today's airplanes are not supposed to rely on a single engine. You're supposed to rely on, I think, at least 3 engines, but I'm not sure about that. Don't quote me on that. Basically, they employ some principle called n-modular redundancy, where essentially they need to have redundant components, n number of redundant components. And dual modular redundancy is essentially the simplest form of n-modular redundancy. You have 2 components. If one fails, the other continues, right? And that was part of the Tesla chip, right? If you remember the Tesla chip picture, we saw that the Tesla chip actually had 2 chips, right? Because if one fails, you continue with the other one. And airplanes are similar. And I think going forward, we need to have more and more of this dependable system solution mechanisms and patchable mechanisms where we are not vulnerable to attacks, even though the attacks may be discovered later on. Okay, can a RowHammer bit flip of an adjacent row? Okay, can a victim row flip a bit of an adjacent row that is not the hammered row? So yes, basically, I think maybe the question is not phrased absolutely correctly, but basically, if you're the aggressor, can the victim row flip? So if you're hammering a row, the adjacent rows get flipped. So hammered row doesn't get flipped because you're hammering the row, you're activating it, you're refreshing the charge. You don't get bit flips on that row. You get bit flips on some other row, basically. So how can you control which bit is flipped in a RowHammer attack? That's very good. Basically, you don't control it. You figure it out. You figure out which bits are vulnerable. And then, based on your beautiful system security engineering capabilities, expertise, science, art, creativity, hard work, etc. Everything else that I talked about when I introduced Calatrava and Frank Lloyd Wright. Based on all of those, you basically trick the system such that it allocates an important data into that bit. And once you trick the system such that it allocates the data that you want into that bit, you can take over the system. And I'd recommend reading the blog post by Google in terms of how to do that. It's not easy, but it requires all the skills that I mentioned earlier. Okay, does ECC memory prevent RowHammer attacks or makes it harder? So that's a good question. So ECC memory today can correct single bit errors and detect double bit errors. We have shown in our works that RowHammer errors can happen in 4 bits and maybe more in the future. So basically, prevents no, makes it harder, yes. But other researchers actually showed that you can bypass ECC if you actually employ everything else that I mentioned again. If you're creative, if you know what you're doing, if you put in the hard work, and yeah, all of those qualities to launch an attack. And those folks actually showed that even though you may have an ECC memory, they can still launch an RowHammer attack in a predictable way. So these are great questions, actually. I'm happy that we're getting these questions. Even though we're running a little bit over, that's fine. None of this is required for anyone. So people don't need to be here. They can also watch it later on. But I think it's important to have this discussion. That's better overall for overall education, I think. Any other questions? So why is DDR4 more probable for receiving RowHammer attacks? So why is DDR4 more vulnerable? Basically, the key answer is if cells are smaller and cells are closer to each other, they become more vulnerable to this disturbance effect. As a result, they become more vulnerable. So as technology node generation reduces, meaning it becomes newer, cells become smaller and cells become better packed. They become closer to each other. As a result, RowHammer becomes a bigger problem. So you can induce these bit flips with fewer number of activates, essentially. And our papers have shown that very clearly. Okay, what if we built faults into our system that we know of? Wouldn't that make our system more secure since we know whether the breach? Okay, so I think this is an interesting idea. So can you somehow build circuits that can quickly identify something is going on and quickly tell you that there's going to be a bit flip? And I think that's an interesting direction. There have been some proposals. If you read our retrospective paper, we actually talk about a proposal that is kind of like that. And I think that's a potentially good direction, but it comes at a cost, of course. But I like that idea, basically. Somehow you build some canary, let's say, canary circuit, and that canary circuit quickly tells you that something bad is going to happen, right? Okay, does this only work with RAM, also other storage mediums? That's a good question also. So I think, so disturbance errors are very fundamental. A disturbance error can happen in any kind of memory. In fact, hard disks were shown to be vulnerable. Flash memory, SSDs are shown to be vulnerable. In fact, we ourselves did a lot of work on flash memory, and we were inspired by our work on read disturbance in flash memory to work on RowHammer. But DRAM is very special because so SRAM, as I mentioned, I think yesterday, it's protected. There's a lot of ECC protection. It's very hard to exploit. In DRAM, there's not a lot of protection. So in commodity systems, you don't have error correction. You don't have refresh rate increase. Basically, commodity systems are not protected. So whenever you get a bit flip, it directly results in a bit flip in your data structures. Okay, so let's see. Maybe someone can help me with these questions because there are a lot of questions now. Can you use RowHammer Spectre for corrupting stored information? Yes. So Spectre, no, but RowHammer, yes. So in RowHammer, you don't need to take over the system. You can just do bit flips and corrupt some information. You don't need to, if your goal is to just corrupt some information, you just keep doing RowHammer, right? And you will corrupt some information. Whereas Spectre, no, you cannot do that because Spectre doesn't really cause a bit flip. Spectre is a side channel. You need to be able to access that private data somehow. That's why it's much harder to launch. RowHammer is you keep doing hammering and you corrupt someone's information and it can lead to a system crash. You can use RowHammer for denial of service, for example. Okay, can't we refresh the rows adjacent to hammer draw predictively? Yes. So that's a question also that was also proposed by some of those access counter-based mechanisms. But of course, that requires also a probabilistic adjacent row activation kind of does that, right? It's kind of if you increase the probability to a reasonable level, you're basically refreshing the adjacent rows, just the adjacent rows with a higher probability because you're activating the victim, activating an aggressor row a lot, right? Because of probabilistic mechanism. If you're activating the aggressor row 1,000 times, based on the probabilistic mechanism, you're refreshing the adjacent rows 5 times, for example, right? Okay. I think I've answered a lot of questions. So I think there was one question, basically, can you, what if, I don't know, I didn't quite understand one question. It's hard to understand, actually. Maybe, can the flip row flip another row? Oh, okay, yeah, no, yeah, that's not easy. I mean, because you're nearly not activating that row. I mean, if you activate that row, yes, maybe, but you're not activating that row. Just by causing bit flips, that doesn't affect some other row, as far as we know. So somebody says, so with RowHammer, we can just cause changes in the system, or can we also passively read data? So passively read data, yes. I think RowHammer can also be used as a side channel. And that was one of the works that I mentioned, also mentioned in this paper. Let's see if I can go to it. It's a Rambleed work. These people have nice names. They basically leak data. So this paper actually talks about how to use RowHammer to read data that you're not supposed to read. So once you have this sort of phenomenon, it can actually lead to a lot of things. Okay, so I think there are more detailed questions that I'm not going to answer. There's one question from YouTube basically asking, this happens, what is the physical phenomenon behind it? Basically, what I described, electromagnetic coupling is one of the physical phenomena, but there are multiple related issues in RowHammer that makes a cell vulnerable. And if you're really, really interested, I would recommend reading our paper. And I would also recommend reading the longer paper that we wrote, which is referenced here, actually, this RowHammer retrospective paper, because that goes into the details, and it also points you to some papers that really discuss the underlying details. But there are multiple reasons. I think electromagnetic migration is one. Conductor bridging that forms between different cells is another one. And also hot carrier injection that also happens. Sometimes you actually inject hot carriers from to a particular location that makes them somehow permanently or temporarily malfunction, and as a result you get these effects. So there are multiple phenomena that leads to it. Okay, are there any other questions? It's good that we had a good discussion, actually. So going once and twice. Okay, it sounds like there are no more questions. So I guess thanks for sticking around. I will see everyone next Thursday, where we will continue with 2 other mysteries, and then we will introduce the labs at that point. Take care and have a good weekend.